So yesterday we began talking about circles. We talked about tangents to a circle. What did we learn about a tangent line to a circle? What's special about it? What's that? What's special about the tangent line to a circle? It intersects a circle in exactly one point. And at that point, what's special? It's perpendicular to the radius at that point. Okay? So if we drew the radius in like we have drawn here, this represents our radius. This line is tangent to this circle, intersects the circle at exactly one point, and at that one point, it will be perpendicular to that radius that connects at that point. Okay? Now you might say, how about the diameter? Yeah, that radius is part of that diameter, so that'd be true also. But we just need to understand that we can draw that radius in there, connect it to the point where the tangent line is intersecting the circle, and those two segments will be perpendicular. Okay? Then we went a step further yesterday, and we said, well, hey, if I have this tangent line, and we say this is tangent right here, but these two tangent lines intersect, then what was special about those two segments? They were congruent. So if we label this A, B, and C, then we're going to say that AC is equal to BC, or segment AC is congruent to segment BC. Those two statements mean exactly the same thing. Okay, since truly this is the definition of each other. I can say, well, how do I define this statement? Well, it means that these are congruent. If I ask how do I define this statement, that would mean that these are equal. Okay? So, that would mean anyway that the distance from A to C is equal to the distance from B to C. Okay? So that's what you talked about yesterday. Go a little step further than that today. We're going to learn more about circles. Okay? So, what's a chord? A chord is a segment whose endpoints are on the circle. Pause while you copy that down, then we'll talk about it. So, can anybody name a chord in this picture? Connor?
Segment AB.
Segment AB. Any other chords in this picture? Magnolia? Segment AC. And do we have one third one? Olivia Howell? Segment BD. All three of those are chords. Okay. Could we draw any chords that aren't drawn there? Anthony? Is there anything there, is there enough information there to draw another chord in that picture that's not already drawn? Like segment D, DC? Okay? Since we don't have E on there, we'll choose one of the ones that, two of the points that are on there. Segment AD, segment BC. Okay, we could draw a few more. Just using the points and the information that's there. So, what's the definition of a chord? Any segment whose endpoints are on the circle. Okay? What if I draw this chord? What do we call that chord? The diameter, because it passed through the center of the circle, right? So that would be the diameter. But it's a chord because its endpoints are on the circle. Any questions on that? Okay, so within a circle, or within congruent circles, three things are true. I'll pause while you copy those three things down. So here we have a picture of a triangle, of a circle with a couple chords in it. We'll label them A, B, C, D, E. So we can talk about them a little bit. If C is the center of the circle, Okay? C is the center of the circle, and we can look at what's going on here. Just to make sure we understand, well, here, let me just stop while you copy this down and then we'll talk. Okay, so just to make sure we understand, this red line here, green now I guess, is a chord. This red line over here is a chord. Okay? On the circle from A to B, that's arc AB. And on the circle from D to E, right here, is arc DE, or ED, whatever. Remember, with arcs, you can label them either way. If it's a major arc, it has to have what? 3 letters. Good. 3 letters. And the middle one has to be the one that's in the middle of the arc. Okay? So it would give a direction in which way you're going around the circle. So, in this picture, if I knew the arc AB is congruent to arc AB is congruent to arc ED, then that would mean that what? Okay, so can you name a central angle?
ACB, DC.
Good. Angle. So if this is true, then our conclusion would be that angle ACB is congruent to angle DCE, or ECD. Okay? I could have said DCE, that'd been okay also. Doesn't have to be in order as long as the middle letter is the vertex of the angle. Okay? And if that's true, then that means that this chord, segment AB, is congruent to segment ED, this one here. Okay? So what this theorem is saying is that any one of these 3 facts is true, then all 3 of them are true. So if next time you look at this picture, let me clean it up for you. If we look at this picture next time, and you see these marks here, that means those 2 central angles are equal, which means then these arcs are equal, or congruent, and these chords are congruent. Okay? So Chandler said it right. If you know one of those 3 things, then you know everything else that we just said is true also. Okay? Now, if they had another one over here, just because I know these are equal doesn't mean I know anything about this segment or this chord or this angle. Okay? Unless they tell me all 3 angles are equal. What would be true if all 3 angles are equal? Then the 3 chords are equal and the 3 arcs are equal. Okay? Good. Any questions on that? Okay, so another rule. Within a circle or congruent circles. I'll pause while you copy this down. Then I'll move it up so you can copy the circle. All right. Here we have 2 chords drawn. We don't know what they're called. It didn't have them labeled, but we have 2 chords here on this circle. And these marks, this one here and this one here, they're kind of blended in the middle of everything else. But those marks mean what about those 2 chords? That they're congruent or equal in length. That's correct. So this theorem is saying, part 2 says if these chords are congruent in length, then that means that they're equidistant from the center. So the distance from here to the chord and the distance from the center to this chord have to be equal in length also. Should be 2 marks on them since I have 1 on the others. Sorry, I had that labeled that way. Okay? And remember, when I have a line and I have a point over here, when we measure the distance from that point to the line, it has to be a perpendicular distance. We can't come up here and measure this and say, well, that's 20 inches. Someone else could come up here and measure this and say, well, that's 18 inches. And then someone else will come up here and draw the perpendicular in and say, well, that's really only 16 inches. You see what I'm getting at? So just a reminder, when they say it's equidistant, they're saying from a point to a line is equidistant. That means they're telling you that that segment measuring that distance is perpendicular to that line. Okay? If I drew in, I highlight that chord and I draw in the 2 radii, right? So radius is the segment from the center to the circle, right? What kind of a triangle is that green triangle? Well, I don't know that for sure. But we do know it's isosceles. He said, if you couldn't hear at home, he said equilateral. We don't really know how long this one is compared to the radii, but we do know the radii are equal to each other. Okay? So we have an equilateral triangle, I'm sorry, an isosceles triangle. Now you got me saying it. We have an isosceles triangle. Remember, a long time ago, we said that in an isosceles triangle, the perpendicular from the base up to the vertex angle, if it's perpendicular, that means it cuts this into 2 equal pieces. Is that making sense? Remember that rule? So that means that these radii are the same, and since we said these distances have to be equal, then when this cuts that into 2 equal pieces, that means all 4 of those equal pieces are equal. Okay? But that's only true if we knew the chords were congruent. Does that make sense? It's only true if we knew the chords were congruent. But what's happening here, I'm highlighting a different color now. What's happening here is we're creating what kind of triangles? Again, I don't think we know these angles. But we do know it's a right angle, so that makes it a right triangle. Now, if these chords, if we don't know if they're equal, then we don't know all these parts here, 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 and here are equal. We still have right triangles. All these little triangles are right triangles. Okay? So some of the problems you're going to be asked to do, you simply have to create right triangles and then use what theorem to find missing parts of them? The Pythagorean theorem. So we're going to be applying a lot of information you learned a long time ago, and that's why I'm trying to make sure it's been put back into your head because you've not used it in a long time. Okay? So again, we have 2 scenarios here. If the chords are equidistant from the center, then the chords are congruent. If chords are congruent, then they're equidistant from the center. So if these distances here are equal, then that means these chords are equal. If we know these chords are equal, then that means these distances here have to be equal. Okay? Any questions on that? All right, let's move on. Yeah. It's our last one. Move this up so you get the 3rd one. Anybody not done with the first 2? still working on the second one. Okay, the first one, just make sure you read my writing, says in a circle, a diameter that is perpendicular to a chord bisects a chord and its arcs. So here we have, in this first picture here, we have a circle, we have a diameter. If this diameter bisects this chord, that means it cuts it into two equal pieces. Okay? Oh, I said it wrong. I'm sorry. What it said is if it's perpendicular. So let me mark it correctly. So it's saying if we know it's perpendicular, okay? So that means that segment AC is perpendicular to segment BD. So if we know this is perpendicular, then that means two things. It cuts this chord into two equal pieces, and it cuts this big arc over here into two equal arcs. Okay? And you might say, well, how about the other arcs? Well, that would be true also. If I know this is perpendicular, then it would cut this arc and this arc into equal pieces. Okay? From the diameter here to that chord. So that's what the first one is saying. The second one says in a circle, a diameter that bisects a chord that's not a diameter. Okay, so if this red line is our diameter, then we're not talking about bisecting this other chord, because diameters would always bisect each other because they always pass through the center, and so that means some of these other facts may not be exactly true. Okay? So we're talking about they're bisecting a chord, so if we say it bisects this chord, so that red diameter bisects that smaller chord, then what's that say? It says that means it's perpendicular. So if I know these are equal, then that means I know this has to be perpendicular. Okay? Same thing over here. If I know this is perpendicular, then that means these have to be equal. All right? Then the last one. In a circle, the perpendicular bisector of a chord contains the center of the circle. So what that's saying, we know that this is perpendicular and these are equal. That makes this red line, or segment, the perpendicular bisector to this chord. Do you agree with that? What this is saying then is that that red segment has to be passing through the center of the circle. The only way it can be perpendicular to that and cut it into equal pieces is if it passes through the center. And now it's not saying it has to be a diameter, because it's possible that it's not a diameter at all, it's just the radius. So all it's saying is that it has to be passing through the center. Okay? It's also possible that it's just a line passing through the circle. Okay? It's possible it's just a line passing through the circle. So all this theorem is saying is if it's perpendicular and if it cuts into equal pieces, it's got to be passing through the center of the circle. Okay, so if we look at this example, and we look at question is, what is AB? Adrian and Chandler should be doing this. What is AB? I think Jared. Okay, let's pause while you talk in your groups for a minute. So Jared's group says it's 14. Jared, can you walk me through why your group thinks it's 14?
Because from the NBC at level 7, so
Okay. So you're saying that this chord, this half is 7. How do you know they're halves? How do you know they're not thirds or 2/3? How do we know it's exactly a half? Brianna, what you wanting to say? Okay. Okay, we said that if this is perpendicular, then this segment has, from the center, the segment has to be cutting this into equal pieces. And so if this is 7, then that makes that 7. Okay, so why does that, Olivia Johnson, why does that make this 14? Just because the other one's 14. Want to take a minute and think about that?
Yeah.
Okay, let's do that. Talk to your groups for a minute on that. Okay, I think Olivia is ready now.
The lines are equidistant from the center.
What do we call those lines?
Chords.
Good. So you're saying these chords, A, B, and D, C, are equidistant from the center. And how do we know they're equidistant from the center?
Because the lines connect to the center.
Because the distance, because these segments connecting the chord to the center both are 4 units, and they're both perpendicular, making them the distance from that point to the line, right? So since these are both 4s, that means these chords have to be the same length. So I totally agree with Jared that the answer to the question is 14. Okay? Good. Do we have any questions? Good job for most of you. I really saw what I want to see today. You took the minute, you discussed things a little bit. When someone found it, you explained to others. Okay? I saw most of you involved in that. That's awesome. All right. Our assignment today then. Lesson 11-2, 1 through 19 all. I actually already did one of them. I should say you already did one of them. That example we just did was, I think, number 4. Okay?